Okay, so let's look at what Howard then did. He focused on this equation that we have got here, where now we are going to say what is happening, what is the relationship between I and S. What happens is S is increasing, and what happens to the number of infections. Obviously, we expect that the number of infections is also going to be increasing, and then it obviously they will get to a maximum, and that's why we're looking for the maximum in the previous video. So we need now to plot that, and we are going to get some curves, the level curves, to say, look, for this value of I, we are going to have this maximum. Then for this value of I, we get another maximum. For another value of I, we get another maximum, and so on. So the level curves were actually given by Howard Ways as follows: to say, look, we are not going to change our initial value for S. Okay, the number of susceptibles is going to remain the same. But what is going to happen is we are going to say the number of susceptibles, and then it's going to remain the same, but what we are going to vary is the number of infected individuals, all right, those in the infected compartment. And you realize that as the number of infected individuals increases, all right, the number of infected individual increases. What is happening is that it is taking it's going a little bit higher. The maximum number of susceptibles has to be a little bit higher not susceptibles rather, but the number of infected, the maximum, to get to the maximum number of infected, it becomes more. If we start with more infected people, then we end up with a higher number of the turning point of our curve. And that makes a lot of sense because we expect that if more people are sick initially with our RE, our effective reproduction number, then we expect that those people are going to infect more people at the same time, rather than as compared to starting with a single individual. So these are fractions. Please take note that these are fractions: the fraction of infected individuals and the fraction of susceptible individuals. All right. So what is going on? What then is going on is the fact that we need to plot this, and we are going to do this in Python. And of course, Howard did not do us a favor of telling us the initial value here. We can try and make it out and see what this is, but it's very difficult to tell. All right, and we have got beta is equals to 1.66 and nu is equals to 0.44. All right, so these are the two guys that we have got. And so we need to do this in Python, and as usual, so let's say this is called, what is this one called? Level curves, all right? So we call this level curves. So we are going to start with obviously importing our NP, all right, our NumPy. So import NumPy as NP. We talked about this. Then from we want to take the ordinary differential equation integration. So we get that from scipy dot integrate. We import. So we are going to import ODE int. All right, and also we are going to import matplot for the plot, right? So matplotlib for the plot, .pyplot. And we are going to this is called PLT in short. So we are just going to import these three, and then we just run this and see if this is correct. Maybe we have got a typo or something like that. And then if there is a green tick, then we proceed. There is a green tick, then we can proceed. I said the other day, you come and open another cell here. But then for now, I'm going to quickly paste my function. If you remember the function that we're having, and we talked about this, the SIR model differential equations. There is nothing that has changed here. Everything is still the same. So we move on, and then we are going to declare now. We are going to declare our parameter values, because we have got parameter values that we want to use. But we need to be very careful. So the parameters that we have, it's 166 and 0.44. So beta is equals to that. And so I was supposed to write in this cell. I'm going to remove it because I don't need it anymore. And then we've got, from there now, we need to be very specific about our time grid. Remember the time grid. But what I'm going to do is I'm going to include the time grid and the various values of, so I want to show you the various values of I. Can you see that the thing that we are varying here is I here, and another initial value of I there, another initial value of I there, another initial value of I there. So I think this is 0.375, something like that. And there is something here, 0.15. We cannot really tell, but whatever it is, it's okay. We can live with that. So I thought it's 0.1, 0.2, 0.25, 0.3, and 0.4. I'm just now using these numbers for the fun of it, to say, look, that's what we have got. We don't know what it is really, but we can live with that. All right, you write what you see. All right, that's what I can say. You write what you see. But the beta we are given, the gamma we are given, all right, or this is the nu, rather, if you want, the v. Okay. And then we run our time space. So we are going to create a figure that has got with so this is just output telling us what is going to happen with our figure. But our figure is 10 by 6, isn't it? So that's what is given there. We are going to have a 10 by 6 figure, and but there is no plot here. All right. So what is this code going to do? All right, for 1000 time points, it is going to compute from 0 to 200, and at the 200th time points, then it's going to compute up to the 1000th time point. And also, what also is going to happen is that the initial value of the infectious I is going to be 0.1. That's the first one. Then the other curve will start at 0.2. The other curve is 0.25. The other curve is 0.3. The other curve is 0.4. All right. And we now need to declare our initial values for our SIR, right? So that's what we want to do, and we are going to do that using a function, because it's better that way. And let's see. So we are going to write a function where we say, look, for I0 in the initial, so I0 is this guy that we were said, whatever value in the initial infectious values, all right? So this is a loop that is going to run, coming to initial infectious values, take I0, and then do this, then come back again, take another I0, then do this, and we are going to have 1, 2, 3, 4, 5 curves. All right. And then obviously we know that if one is infected, the total population, there is nobody who has recovered, so it's 0. So the total population will simply be S plus S0 plus I0. All right. So in order for us to see how many people are actually in S0, we must remove those that are in I0. What I'm saying is that if we have got no recoveries, but we had 100 people susceptible, if one is infected, then 99 are susceptible. So that's what we are doing here. All right. And here we are given that S0 plus I0 plus R0 is equals to 1. So I need to make this to be a 1. That's a mistake there. I need to make this to be a 1, like that, because it's a fraction, right? A fraction that adds up to 1. So if we then run this code, remember this is our symbolic representation of this matrix, this row vector that contains our initial values. So we are going to run this. Nothing is supposed to happen except for the green tick to say, look, thank you, you have done well. But I hope you have understood what we are doing here. This function is taking I0 from up here. So it's taking I0 from up here and checking what's happening here and plotting. And then when we plot, you're going to see the plots for each I0 that we get from there. Okay. And then now I create another cell so that now in this cell we are going to get our solution. Remember that solution that I actually gave to you the other day? And I said, look, we can actually ask for what is the problem here? The problem is indentation. There is a function here, f, and s solution is starting from there, so I need to take it back like that. Then I run again. It's still so it's saying there is derive that is not defined. Didn't I define something called derive? I think we did. Here it is. Oh, we didn't run it. We just wrote this function, but we didn't run it. Okay, now it has been run and we've ran it now. So yeah. So let's see if this is still a problem. Yeah, now it's fine. Okay. So can you see that if you don't run a cell, then it is going to have an effect on the other cell as well, because that's how it works. So now after doing that, we have solved. Again, do like what I did the other time. I said I simply wrote solve so that I can get the solution. And if I run this thing, it's going to give me a table. I mean, lots and lots of numbers, because it's going to look at every time point and say what happened. So these ellipses that we have here, these 3 dots here, they're showing that it's a lot of numbers and they go to the 1,000 time points. So we don't need this. We rather plot. We would rather plot. All right. Because what is happening now in the plot is it's looking at each and every 1, 2, 3, right? So it's looking at each and every, say, time point 1. Then the plot is 1, 6, 2, 4, 3, 0. That's how we get the plot, right? And then the second plot, the third plot, and so on. So, but we don't want this. What we want is to actually get the plot itself instead of getting those solutions in that particular way. All right. So now let's plot, and our plot is not going to be any different. Well, you can see that there might be a problem with indentation there. Let me try to run. You can see that the error has been highlighted as well already before doing anything. And let's see if we run, what's going to happen. What's going to happen is there is an unexpected indent, because this thing is just way inside there when it's supposed to be out there with the others. And let's see now, if I click there, now you can see that it's gone. All right. So our plot is going to check for I0, and it's going to plot the I0 for 5 rather. Going to give us 5 level curves, and the x-axis is the susceptible, the y-axis is the infectious class, and then the title of the plot is SIR model phase plan for different initial values of infections, right? And then we want the legend. We need to see what's going on there. As you can see in the graph by Howard, there was no legend. He didn't tell us what's going on, what these values are. They didn't tell us anything. So we want to avoid that. So we want to see the legend. And then plot show simply says means that show us the plot. So let's run this thing. And then if we do that, we are going to get something like this. Okay. So now what we have here is our curve for I is equals to 0,4. That's what we have. And I wonder why we have that only. I wonder why we have that only, because it was supposed to give us for I is equals to for I is equals to the various values that we have got there. I'm just, let me just run it again. Okay, it's still giving us that. So it means there is a problem somewhere, obviously. And let me see if I can find the problem quickly. Let me just do this. All right, this is the plot that we have got. And then we are running this code. All right, it's still giving me the problem. My legend obviously is showing for 0,4. Let me see. I changed something along the way. I changed my initial value here. All right, that is okay. There is no problem there. And what else did I do? I did something. No, I didn't do anything. But all right. So we have got that, we have got that, then we've got this. All right, let me just run everything again. So that's the challenge that you can face if you make some changes to your code. You might end up getting something else different, representing something that is not what you intended to get from the onset. All right. So it seems as if we have got a challenge here with. Let me refresh. So you can turn runtime restart session. You can come here and restart the session, because it might be that there is some cache or something taking place. So let me run restart session again. Restart session and run all. All right. So I've restarted that. Now everything is running. Let's see if this is going to give us some good changes. Nope, it's not giving us anything. It's not a train smash. These things, they do happen when you are coding. All right. Things don't go your way sometimes. What happens if I write the whole code in one block? Let me do that quickly. I'm going to write the whole code in one block, and then this is what I'm expecting to get. Let me put back here and say 1.1, because that's the only thing that I changed. All right, then I run again, then I run again. Okay, so there is a problem with this code that we are writing in pieces, which is okay. These things, they do happen, like I was saying. But this is the same code, still the same code over here, but it's in one block, and it's not supposed to give anything different. All right. And also, this shows the reproducibility of the work by Howard. All right. This is the reproducibility of the work by Howard. We can actually reproduce his work, which is an excellent thing.